Good morning all, I am Ron Francis from the Electronics and Communication Department, Semester 7 Batch B, and my guide is Assistant Professor Rinsimaran Varki from the Electronics and Communication Department, SCCT Pali. And the topic of the seminar is Wearable Thermoelectric Generators. So these are the contents included in the seminar. First of all, we will have a brief introduction on what is meant by Wearable Thermoelectric Generators or TEGs. Then we will see the timeline of the TEGs. Then the Seebeck effect, which is the guiding principle behind the working of the TEGs, and some of the details regarding the basics of thermoelectric generators, the application of TEGs, the need for wearable thermoelectric generators, some of the considerations we take into account while making TEGs wearable, the working principle of wearable TEGs, some of the details regarding efficiency of TEGs, types of wearable TEGs, application of wearable TEGs, challenges faced while advancing in this domain, and some of the material and manufacturing advancements, and finally the conclusion. So coming on to the introduction, wearable TEGs are special type of devices which are capable of converting body heat energy into usable electricity. So heat energy to electricity conversion, this is what is done by diesel generator or such devices, but in contrast to such mechanisms, thermoelectric generators or TEGs does not have any moving mechanical parts. So in a diesel generator we have a moving mechanical system which does convert the heat energy into mechanical energy and thus to electrical energy, but in contrast to such system, the thermal generators are capable of converting the heat energy supplied directly into electrical energy without any moving mechanical parts. And this works on the principle of what is called the Seebeck effect, and more details on the Seebeck effect will be discussed in the coming slides. So coming on to the timeline of the thermoelectric generators, it's in 1821. The German physicist Thomas Johann Seebeck, he made an observation, and it is called the Seebeck effect. And more details will be discussed later. And for over a century, there were no much advancements in the energy generation capabilities of the Seebeck effect. But by 1930s to 1960s, the bismuth telluride and lead telluride were used for the manufacturing of thermoelectric generators, and they find applications in radioisotope thermoelectric generators. So in these applications, the TEs are used for converting the heat energy radiated by radioactive elements directly into electricity. And by 1960s to 1970s, some of the improved TEG designs were suggested, and they find application in powering remote weather stations. And by 1980s to 1990s, the thermoelectric coolers or TECs come into existence. These are devices which does work on the direct opposite principle of thermoelectric generators and what we call the Peltier effect. By 2000s, the hunt for renewable energy resources began, and TGs find application in converting the waste heat from the engine directly into electricity. So, in coming into the case of an IC engine, it does have an average efficiency of about 20 to 25%, and more than 50% of the heat is liberated through the exhaust or wasted through the exhaust. And TGs find application in converting this wasted heat into electricity, so the overall efficiency of the engine can be improved. And by 2005, TGs find application in remote power generations, and by 2010 some of the wearable TG prototypes were developed, and especially for the healthcare and military applications. And by 2015 the commercialization of the TG happens and TG products starts to hit the market. And by 2020s the integration of thermal generators into wearable technology happen, and at present researching materials and structures for TG efficiency improvement. And the Seebeck effect, as we have already discussed, the Seebeck effect is the basic principle behind the working of the TEG, and we have already discussed it's an observation made by the German physicist Thomas Johann Seebeck. And according to this effect, it says that the temperature gradient across the junction of two dissimilar conducting materials produces an electrical voltage. What it says is that, as we can see in the figure, there are two dissimilar metals, metal A and metal B, and they are joined at two junctions, junction 1 and junction 2, and one junction is at higher temperature considered to the other. So in such a scenario, a voltage will be generated across the two junctions. This is what the Seebeck effect says, and the voltage produced is proportional to the temperature difference and is characterized by a material specific property, what is called the Seebeck coefficient of the material, and it is represented by the letter alpha or S. And coming on to the basics of thermoelectric generators, so TGs, these devices are built using special type of materials, what is called the thermoelectric materials. So these materials are special materials which has special properties such as high Seebeck coefficient, low thermal conductivity, and good electrical conductivity. This combination is crucial for the efficient thermoelectric conversion, and some of the examples of the materials which hold these properties are bismuth telluride and lead telluride. And we have discussed about the materials used for building thermoelectric generators, and to the observations made it is found that mostly semiconductor materials hold this property to a great extent. So rather than using two dissimilar conductive metals, what we normally use in practice is that we just select a semiconductor material and dope it with p-type and n-type elements to make it two dissimilar materials. So the p-type elements are made of semiconductor materials doped such that the carrier charges are positive and the Seebeck coefficient is positive. The n-type elements are made of the semiconductor materials doped such that the carrier charges are negative, that is electrons, and the Seebeck coefficient becomes negative. So the overall one is positive and the other is negative. So the overall Seebeck coefficient of the system adds up, and we will get a higher voltage. And coming on to the structure of the thermoelectric generators, so we can see that the thermoelectric material pairs or the pillars of the TGE are connected electrically in series and thermally in parallel, and the heat plate is connected in the spot of the series joining so that the heat is delivered to the pairs. A heat sink or cool plate is connected similarly to the other side. As we can see in this figure, the N and P pillars are connected electrically in series to the external load and thermally in parallel in between the heat source and the cool side of the thermoelectric generator. And coming on to how the energy is generated in a thermoelectric generator, one side of the TEG is exposed to the heat source, the hot side, while the other side is kept cool, the cold side. And as you can see in the figure, there are two pillars, N-type and P-type pillars. And in case of N-type pillars, when the N-type, one side of the N-type pillar is exposed to higher temperature, the electrons they achieve higher kinetic energy and move to the cooler side of the N-type material. But in case of P-type material, the holes move to the cooler side of the p-type material. So there is an higher concentration of holes in the cold side of the p-type material and higher concentration of the electrons in the colder side of the n-type material. So this potential, there exists a potential between the colder side of the p-type and n-type material, and electrons from the colder side of the n-type material flows to the cooler side of the p-type material. This is how the voltage or current voltage is generated across the thermoelectric generator, and the magnitude of the voltage generated is determined by the Seebeck coefficient alpha of the thermoelectric material and the temperature difference. So, and the Seebeck coefficient is given by the equation alpha is equal to minus delta V by delta T, and the unit of the Seebeck coefficient is in microvolt per Kelvin. So we have discussed some of the basics related to thermoelectric generators, and coming on to the applications, TGs find application in power generation in remote off-grid locations, waste heat recovery in industrial processes, automotive exhaust heat recovery for improved fuel efficiency, applications in aerospace to power instruments on spacecraft, and some of the portable electronic devices and sensors. And here we have a schematic of commercial TEGs, and we can see that how the pillars are arranged in electrically in series and thermally in parallel manners. And coming on to the need of wearable energy harvesting. Wearable energy harvesting refers to the process of capturing and converting ambient energy from the wearer's environment into electrical power to supply and prolong the operation of wearable devices. And the needs for making advancements in this field is the extended battery life in wearables. So wearable TEGs can be used to extend battery life in wearables. The sustainability, that is energy sustainability, user convenience, the recharge cycles can be reduced to a great extent, and continuous data monitoring, healthcare and medical applications, wearable electronic integration. And these are some of the considerations while making TEGs wearable, and those include miniaturization and compact design of the TEGs, the flexibility of the TEGs, integration with clothing. So TEGs should be able to integrate with existing clothing materials, and variable heat source optimization. This is one of the most important consideration we take into account while making TEGs. So human body, the heat in the human body is varying with time to time, and the TEGs should be optimized to provide maximum efficiency in all these varying temperatures, and low temperature operation, user comfort and safety, efficiency optimization, etc. And coming on to the working of TGs, it's similar to what we have discussed in the bulk TGs, and the average temperature of the human body, as we can see in the figure, is about 37 degrees Celsius, and the average temperature of atmosphere is about 20 to 25 degrees Celsius. So there exists an average of about 10 to 15 degrees Celsius in between the human body and the atmosphere. So TG utilizes this temperature gradient which exists between human body and atmosphere to generate electrical voltage, and the voltage generation is same as that of the bulk TGs, and only the material structure and the generation capabilities differ in case of TG. So coming on to the details of the efficiency of thermoelectric generators. Before discussing efficiency of thermoelectric generators, we need to see into another term called the figure of merit of thermoelectric generators. It's given by the letter ZT, and the equation is S square sigma T divided by K, where S is the Seebeck coefficient in microvolt per Kelvin, sigma is the electrical conductivity in Siemens per meter, K is the thermal conductivity in watt per meter Kelvin, and T is the absolute temperature in Kelvin. And this the figure of merit gives a more broader idea related to the efficiency of TEGs, and the Z of T, or the figure of merit, is used for designing the TEGs for specific applications, such as the changing the electrical conductivity changes the value of the figure of merit, and changing the thermal conductivity also changes the value of figure of merit of a material. So thermal conductivity is varied by varying the structure of the thermoelectric generators, and the electrical conductivity can be varied by varying the doping concentration of thermoelectric generators. And as an example, we have bismuth telluride, a graph of bismuth telluride here, and in the x-axis it's given the temperature difference between the two poles of the thermoelectric generator, and the y-axis gives the percentage efficiency of the system. And inside we can see the different values of ZT for the same material, ZT equal to 2, 1.8 and zero point 0.5, and we can observe from the graph that the percentage efficiency of the system comes down as the value of ZT goes down. And it can be also observed that the maximum percentage efficiency of the system is far beyond the Carnot efficiency of the system. So normally TGs achieve only a maximum of about 10% efficiency. And at the bottom table we can see examples related to different materials and their maximum efficiency, and how it improves with respect to the improvement in the figure of merit values of the material. And coming on to the type of wearable TGs, this is a classification based on the power density of wearable TGs, and they are basically classified into three, that is low power, medium and high power wearable TGs. So in low power wearable TGs, the power output is less than 1 watt per centimeter square. Even though it says it's less than 1 watt per centimeter square, these devices are capable of fully producing about watt in the range of milli or micro, and the applications are fitness trackers, smartwatches, health monitors, and low power IoT devices. That is mostly for low power applications. And coming on to the next classification is medium power wearable TGs. So these are TGs which are capable of producing energy in the range of 1 watt per centimeter square to 10 watt per centimeter square. And the applications are medical devices, example implantable devices and communication equipments, industrial wearables, portable sensors, and data loggers. Coming on to the third classification, it's the high power wearable TGs, and it's less common in wearables, and it's more bulky device, and these devices are capable of producing energy in the energy more than 10 watt per centimeter square. And some of the applications are specialized military gears, emergency response wearables, etc. And coming on to the application of wearable thermoelectric generators, the TGs find applications in healthcare and medical devices, glucose monitors, electrocardiogram or ECG sensors, pulse oximeters. And coming to the fitness and sports monitoring domain, they find application in the heart rate monitors, pedometers, and in the military and defense domain, the power sensors and communication devices for military personnel. And in the consumer electronics, there serve as a backup power source for consumer electronics like smartphone, smartwatches, and headphones. So coming on to the challenges faced while advancing in this domain, and some of the challenges are limited temperature gradient. The temperature difference between the body and the ambient environment is relatively small. We have already discussed details regarding that. It's a maximum of 15 degrees Celsius which exists between the human body and the atmospheric temperature. So typically this limits the potential of the power output of TGs, making efficiency a critical consideration. So the TG efficiency should be modified accordingly to work in lower temperature gradients. And the second challenge is the skin comfort. TGs must be designed to be comfortable and non-irritating to the skin. Materials and form factors need to be prioritized user comfort and durability. And coming on to the third point is efficiency. Maximizing energy conversion efficiency is essential to ensure that TGs can generate sufficient power for wearable devices with the low power requirements. And temperature regulation. Maintaining a stable temperature gradient is challenging as the body's heat production can vary based on activity, clothing, and environmental condition. This is also what we have discussed earlier already, and where we see that your human body temperature can vary according to the state of the human body and the surrounding temperature. So TGs should be optimized to work in all these conditions. And coming on to the advancements made in this field, and first of all we'll see the material advancements. And first is the flexible thermoelectric materials. Traditional bulk thermoelectric materials are rigid and not suitable for wearable applications, and advancements in flexible thermoelectric materials such as organic based materials and composites have enabled the creation of TGs that can conform to space of human body and can be integrated into clothing. And some of the examples are bismuth antimony alloys and P3HT. It's an organic compound. And coming on to the second advancements, nanostructured thermoelectric materials. Nanostructuring thermoelectric materials at the nanoscale has led to significant improvement in their thermoelectric efficiency. Nanostructured materials have enhanced Hebert coefficient and reduced thermal conductivity, resulting in higher energy conversion. So nanostructuring, the main purpose is to reduce the thermal conductivity of the material. And some of the examples of the materials which can be nanostructured are bismuth antimony alloys, silicon germanium alloys, etc. And coming on to the third advancement is low-grade heat harvesting materials. Researchers have developed thermoelectric materials that are optimized for low temperature differences, such as those found in body heat powered TGs. These materials are designed to operate efficiently at a relatively low temperature gradients. Some of the examples are COSB3, PEDOT PSS, that's an organic compound, PBTE, and PBSC. And the fifth one is thin film thermoelectrics. Thin film deposition techniques such as sputtering, it's a physical vapor deposition technique, and chemical vapor deposition technique enable the fabrication of compact and lightweight TGs. Thin film thermoelectric materials can be integrated into wearable textiles and fabrics. And the last one is flexible substrates. Advancements in flexible substrates including polymers and textiles have made it possible to create flexible TGs that can bend and stretch without compromising their performance. And coming on to the manufacturing advancements, so these are some of the advancements in the manufacturing sector related to thermoelectric generators, such as for commercial production and rapid prototyping techniques, etc. And first of all, the printable electronics technique. The printable electronics techniques such as screen printing have been employed to fabricate TGs on flexible substrate. This allows for cost-effective and scalable manufacturing of wearable thermoelectric generators. The second point is hardware production or roll-to-roll production. It's a manufacturing process which enables high volume production of flexible TGs. Hardware techniques are well suited for continuous and efficient production. The first 2 point is related to the bulk production of TGs, and the third one come into play when in the stream of research and development of TGs and additive manufacturing techniques. 3D printing and other additive manufacturing techniques are used to create complex TG geometries and structures, allowing for customization and rapid prototyping. So rapid prototyping and customization is required highly for the research and development of TGs and testing their efficiencies. So the additive manufacturing improvement in additive manufacturing techniques is a boon to TG research and development. And the next is integrated design. TG manufacturing has become more integrated with the thermoelectric material. Heat sinks and insulation layers being combined into compact and efficient modules. So integrated design, what it does mean is that the heat sinks and kind of devices is integrated directly or built directly into the TG structure rather than going for a different device or another material. The structure itself is compatible to provide heat insulation and kind of things inside the design structure itself. And finally, the cost reduction. Advancement in material and manufacturing have contributed to cost reduction, making wearable TGs more economical, viable for mass production and commercialization. And these are some of the companies included in the research and development of wearable thermoelectric generators, and those include Perpetua, Thermidas, NASA, Northwestern University, University of California, Los Angeles, Harvard, and MIT. And coming on to the conclusion, as research and development in this field continue, wearable TGs are forward to play a significant role in powering wearable devices, enhancing user convenience, reducing electronic waste, and contributing to sustainable energy practices. And we can hope to expect the TG devices fastly in the market. And thank you all for your patience. So these are the references I used to build this presentation. Thank you all.